So we're going to start the case study session, only one session. For mass spectrometry analysis of glycoconjugates or glycopeptides. It's being more specific. So I was asking Robert, what is important now is that you really follow what's going on. So if you're lost, please raise your hand, and the idea is to be very interactive so we can all, and I include myself because I am also a novice on these things, understand what's going on, and most of all, be capable of, if you're not going to be doing yourself mass spectrometry, at least be able, when you see a profile or something, somebody's telling you, oh yeah, this is good, looks good. Okay. Thank you, Robert. And, ¿estás grabando, Omar? ¿Vas a grabar? ¿Vas a grabar? So then, since there's an internet recording and they need to listen to you, I know it's a little bit awkward, but it'll be good if you use the mic. So I'm going to ask Katia.
Okay. So we're going to go through some LC-MS data here. So this is a complex mixture that has been separated by reverse phase chromatography, and as the peptides elute off the reverse phase column, they're being introduced into the mass spectrometer. And so this first slide here is showing a mass range of precursor ions that are eluting at this particular time point. So at this particular time point, each of these peaks, this one here, this one here, this one here, even the ones that aren't labelled, each of these correspond to a different peptide that is eluting at this particular time point. And so for several of these peaks, I've got labels on them that say an M over Z and a Z. So in mass spectrometry, you're not measuring masses, you're measuring mass to charge ratios. So for this particular peak that I've highlighted here, this one has a mass to charge of 1100.5, and it has a charge of 4. Z equals 4. Oh, this isn't working very well. Z equals 4. So in order to work out what the actual mass of this particular peptide is, so this is an M plus 4H4 plus. So it's got 4 protons attached to it. So to calculate the neutral mass, I'm going to take the 1100.5, I'm going to multiply it by 4, because it's got 4 charges, and I'm going to take away the mass of the 4 protons to get the neutral mass. So this particular peptide has a mass of 3,398. And so this peptide was fragmented by ETD, electron transfer dissociation, and from the database searching, using the methods I talked about yesterday, with this mass modification searching, this is the match that it came back with. So it said, this is what it thinks the peptide is, and it's put a mass modification of 1241 on the asparagine. And down here, it's annotated which of the peaks it's been able to explain on the basis of these fragment ions. So the Z3 ion, to remind you, is 3 residues from the C-terminus, so it basically corresponds to QIR. Then the Z4 is going to be SQIR. Z5 is going to be ASQIR. And then we have some C ions going from the other end, C3, which is going to be EGS, C4, EGSR, C5, EGSRT, and so on. You've got the idea. So the first question is, what is 1241? I'm going to go through and go through the first part of the talk, and then we'll go back and try and work out how to answer some of these questions. So this is the same spectrum as we were looking at earlier, and if you remember from my talk yesterday, neutrally charged glycopeptides generally co-elute. So the question is, are any of these other peaks that we're seeing in this spectrum differently glycosylated versions of that same peptide? And so 10 of the peaks in this spectrum, the 10 I've labelled in red, were actually fragmented. And so we have we have MSMS spectra, fragmentation spectra of those 10 peaks. And so the next challenge is going to be, can we work out which ones of these are other glycosylated versions of the same peptide, or whether some of these are unrelated peptides. So the next slide here is showing the CID spectrum of that same peptide, the same one that we've just shown. So if you remember, in CID spectra, we don't get very many peptide backbone cleavages. We mainly get fragmentation of the glycan itself. So based on this, the next question that I'm going to ask you is, can you explain any of the peaks in this spectrum? And then the next few slides contain the other 9 MSMS spectra from the precursors that were selected at that same time. And so the next question is going to be, can you do any of these look like other glycosylated versions of the same peptide, and can you come up with a sugar composition to explain them? So how are we going to answer these questions? So one piece of software that I highlighted yesterday that's going to be helpful is this one here. I've given you the web address, and so this is a program where you can try and work out what the mass shift you're seeing corresponds to in terms of glycan sugar units. So you can if we go to the web, well, I mean, we have the internet, let's go to the web page. So if we have the web page here, we can say, well, if I had an NSR hexosamine, that's going to give me a mass of 203. If I had another one, that's going to be 406. And maybe I want to add a hexose, 568. And so going through and clicking on different combinations of this, you should be able to work out what these different mass shifts correspond to in terms of glycan compositions. And so if you remember from one of the earlier slides, we had a 1241. So using this piece of software, we should be able to try and work out what that 1241 actually is. And then for these other peaks, we've got M over Z's and Z's, so we can work out what the masses of these different peptides are. And so based on the mass differences between the mass of this unmodified peptide and the masses of these peptides, we can try and work out what the sugar compositions are of these different peaks. So I'll just go back to And so the other program I'm highlighting here is this program called MS Product. And so this can be used to tell you what the masses of the potential fragment ions would be from the peptide part of it. And so, okay, well, we've got the internet, let's do it itself. So this is the protein prospector, and I was clicking on MS Product, which is here. So I can type in the sequence of the peptide, which I can't remember. So I've typed in the sequence of the peptide here, and I've put this mass shift on the N, and then I can tell it what type of fragmentation I used. So if I told it was ETD, it's going to give me a list of the potential fragment ions I might see. Oops, that's not ETD, what's it done? Okay. Click on that. So it's going to give me the list of what the potential B's, C's, Y's, and Z's are here. So if I pull up the spectrum I had at the start, oops, that's yesterday's talk. screen's not really big enough. Just about. So you can see that we have this peak here at 400.35, and in my list it tells me that's the Z3 ion. And so this is basically a table that is explaining what all these potential masses would be. 663 should be a C6 ion. Yeah, there it is. And so you can also do the same thing, telling me that it's CID data. And so now it's going to tell us the B and the Y ions, because that's what we're going to expect from CID data. But this software is not intelligent enough to know that the sugar is going to fall off. So what might be useful is to look to see what the masses would be if the sugar was not attached. Or more significantly, seeing it's an N-linked glycosylation, we're going to expect that first hexnac to remain attached and the rest of it is going to fall off. So I can actually tell it hexnac, and it's going to give us the masses of fragments we might expect. I'm going to do a little trick and tell it could be up to 4 parts. I'll show you why. So here it's going to give us what potential masses we might expect from the CID data. And we had a CID spectrum. And you're going to find that virtually none of these peaks can be explained. I doubt. Let's see, 1297 3 plus. Oh, that's going to be very big. But what peaks would we expect to see from a CID spectrum? Can people remember from yesterday what we'd expect to see?
There is a fragmentation in many different linkages of the glycans, so you expect that you get the sequence of the peptide, but there is some ions, oxonium ions.
Yep.
So you can know that peptide is glycosylated, but you cannot tell what is the glycosylation.
Right.
That.
Okay. So yes, you're correct. You're going to get some low mass ions. So this 204 here is the hexnac oxonium ion. So it's telling us that there is a hexnac in there. And this 366 is the hexnac hex. So that's another glycan fragment. And then the only other peak in here that I would expect you to be able to explain is this 1121. If you remember, the other big peak you should see is the intact peptide with the hexnac still attached. And so we've got 1121.21. And up here, hopefully, okay, so it should be 1120.87. It's actually the second isotope. So that peak corresponds to the intact peptide with one sugar attached. And that's what you should see for all of the glycopeptides with this particular peptide on it. So all of the different glycosylated versions of this peptide should all produce this 1121 peak, and they all should all produce these low mass fragment lines. So here's the first 3 spectra. Which ones of these do you think are differently glycosylated versions of the same peptide? Any ideas? Do you think this top one is a differently glycosylated version of the same peptide? Who says yes? I don't. So this top spectrum doesn't contain this 1121. So, and it also looks a little bit different in the low mass region in that it's got a very big 274, which the last one didn't. So this is a glycopeptide, but it's not the same peptide because it doesn't have the 1121 peak in it. The second one? Yes, okay. So the second one is another version of that same peptide. And so this is the 1049 peak. Down here. So the 1100 was the one we were looking at before, and this is the 1049. So the next question is, can we work out what the mass of the glycan is on this particular peptide?
I have a question before that. If you go back, and this is probably a stupid question because I understand this 1049, 1094 is the mass of the original peptide?
Mass to charge, yes.
Oh, okay.
Yeah.
Okay, then I understand.
Yeah, sorry, yeah.
No, that's.
I should have
just
put.
Thinking.
I should have put the charges on.
Okay,
here. You're right.
That's good.
Yes.
Thank you.
So this, 1049 is down here, and it's got a charge of 4.
Okay, that's why that mass is smaller than the
Right.
peptide.
Yes. So this peptide is smaller. In terms of M over Z, it's 51 and a quarter. But these are quadruply charged peaks. So the mass difference is actually 51 and a quarter times 4, which is 204. Is that right?
Yeah.
Okay. So this is a smaller glycan. Can we work out what the structure is? Well, the first thing we should probably work out is what is this 1241? So we'll click through and see if we can come up with a composition. Oops. So we've got two hex next. So all these end-linked glycosylations. That's the sort of three main types of glycosylation structures you're going to get, and so it's going to be a subset of one of these structures. So all of these structures have a similar core, so that they've all got 2 hexnacs, and then they've all got various numbers of hexoses or hexnacs afterwards. So we know it's going to have at least 2 hexnacs, and then it's
You can put it at least, then that's good enough.
So I mean.
It should be like the minimum number of what you think.
Yeah. So I mean, I know I want to have at least 2 hexnacs in here. So what I could try keep adding hexoses and see if I get to 1241. No, I don't. So it's not all high manus. So therefore, there's going to be something else in there. Let's try putting another N-star hexose in. That's very close. Oh no, it's 1241 we wanted, isn't it? 1241. So that doesn't match either. So maybe it's got a fucose in there. Hurrah! Okay. So it's got a composition of 3 NSR hexosamines, 3 hexoses, and a fucose. So it's going to be, there's going to be 2 hexnacs, 3 inositol, or 3 hexoses, there's going to be a hexac on there, and there's going to be a fucose coming off the side, probably. So we've got a composition for the 1241.
What information did you give before? When did you give the web page the mass of the peptide?
I didn't.
Okay.
So
just the difference.
This is just calculating the mass of the
glycan.
glycan.
Okay.
Yes.
So then you add that to the peptide.
Yeah.
Okay.
So from the software came back with an answer that said, this is the peptide sequence, and the mass of the glycan is 1241.
Okay. So then you look.
And so then we're trying to come up with an explanation for the 1241.
Is there a unique combination that gives you that 1241 in the software? I mean, you can start maybe with sialic and exos and go to 1241.
So is there software where you can put in the mass and it'll come back with a composition?
Yes. I mean, you started with maybe with exos, I can't remember right now, but you get to 1241. Is there a way to get to 1241 if I add maybe, I don't know, 5 sialic acids? I don't know if I'm clear.
No. So, one, there isn't a way to get to 1241 using 5 sialic acids, and 2, we know what sugar structures in general are possible. So, we know that it's got to have a structure somewhat similar to this, because all ending glycans start with this same base build. So, I mean, there are possibilities with certain masses that you could get 2 different compositions. For this 1241, I don't think there is, but you could potentially come up with more than one composition that has the same mass. So for ending glycans, they all have this same sort of starting structure. For O-linked, I mean, there are known O-linked structures, but they don't. They're often a lot smaller, and you don't have the same sort of building blocks. I mean, most O-linked structures are starting with N-acetyl galactosamine, but beyond there, you don't know. So we've got this 1049.25, and we want to try and work out what the sugar composition of that is. So here's our peptide with the one hexac still attached. So the first thing is we want to work out what 1049.25 is if it was singly charged. So let's find a calculator somewhere. So 1049.25, and it was quadruply charged, so we're going to multiply it by 4. And then I'm going to take away, I'm going to take away 3, so it would be that That's what the mass would be if it was singly charged. Where the mass of this singly charged with one hexagonal attached would be 3360, and we've got 4194. So take away 3360. So it's 834, and this has got the hexagon attached. So if I add 203 on again, would have the mass of the whole sugar. $1037. Have I done that correctly? I hope so. That doesn't sound right.
Sorry to interrupt, but
Yep.
I can't understand what are you doing now.
Okay, so no, that's fine.
This part.
Yeah. So we've decided that this particular peptide is a differently glycosylated version of the other one that we've already identified. And so what I'm trying to work out is what is the mass of the glycan on here, because we know what the mass of the peptide component is because we've got the peptide sequence. And so I'm trying to work out what the difference in mass is between this peak that I've seen and the mass of the peptide on its own. So, I mean, let's get rid of all the modifications. So the mass of the peptide component on its own is going to be this, whatever this tells me. So the mass of the peptide on its own is 3,157. So the peptide part has a mass of 3,157, and our peptide in total, it was 1049.25, wasn't it? Use its calculator. It's clear. 1049.25. Quadruply charged. Take away 3. So the mass of this peptide in total is 4,194, of which 3,157 is the peptide, and so the difference between those two should be the mass of the sugar. Yes. Which is 1037. So can we come up with a composition that's 1037? Let's go back to where we started from. So it's not hexosamines and hexoses, but if I do that, I suspect that's what it should be. Why is it not 5.1 actually? Somewhere we've lost one mess unit. It should be 1038. Why is that? I mean, this is the 204 less than we had before because we've got rid of the 1N-star hexosamine. So this should be the sugar composition for that particular peptide. So we've got another spectrum here. Does this look like the same peptide? Yes. Yeah. So we've got a big 1121 again, and we've got the same low mass peak. So this is going to be another glycosylated version of the same peptide, and this the 1094 is quadruply charged, so it's 6 1/4 less than this one here. And so it's going to be 25 less in mass. So I remember that this one had a mass of 1241, the sugar. So this is going to be 25 less. 1241, take 25. So that's got a mass of 1216. The sugar has a mass of 1216 on that one. And so we can get to 1216. So that particular peptide has hexanak 2, hex 5. So that's a high manners type structure. No. So it's going to have 5 manners. So we don't have information about the linkage here. So I can't tell you whether it's 2 on here and none of these 4 there, or whether it's 1, 2 here, or any other combination. We've just got a composition.
Is there any limit for the structure you can identify? For example, in high molecular mass of the glycan and glycans, I mean lactosamine glycans. After you have the complex glycan, then you can have lactosamines.
Okay.
Or gal 1,3 bonded galactose. You can identify that glycans?
In theory, you should be able to. If you get a decent enough, if you see the precursor peak, you should be able to work it out on the basis of the mass. Yes, providing you get a fragmentation spectrum so that we can say that it looks like it's the same peptide.
Okay.
Yeah. So we've gone through these 3 and decided that the first one is a different peptide and the second 2 are the same. These are the next 3 spectra. The top one, I think everyone's probably going to agree, it's the same peptide again because we've got this big 1121. So this 1120 peak, if we look, this only had 3 charges. So this is actually quite a bit smaller peptide. So the mass of this is going to be 1120 times 3, take 3, roughly. So it's going to be 3,360, roughly speaking. So this is quite a lot smaller. Well, let's not do roughly speaking. Let's do it exactly. 1120.88 times 3. So the mass of this glycopeptide is 3360. And the mass of the peptide alone is 3,157. 3360 minus 3157. 203. So that's just got a single hexanak on it. So if you read the literature, you wouldn't expect to see an N-linked sugar with a single hexanak attached. But when we do this glycopeptide analysis, we quite often find these. And us and other groups have commented on seeing these a lot. And so why do other people never see these? The reason is they're normally releasing the glycans and then trying to analyze them. And if you've got a single hexanak, that's not retained on any of their systems. It just flows through because it doesn't bind. And so any anybody doing glycan analysis never finds these very small structures because they come through in the void volume in all the chromatography they do. Okay, so that was the 1120. Then we've got an 1135, and again we've got a big 1121 peak in there. So this is another version of that peptide. The 1135. Okay, so it should be 1134. 1134.7 was quadruply charged. So this is now a much bigger structure again. So 1134.76 multiplied by 4. Take away 3 to give it the singly charged mass. So this has a mass of 4,536, and the mass of our peptide alone is 3,157. If I take away 3, 1, 5, 7. So the mass of this glycan is 1379. I think it should be 1378. I must have lost a decimal place somewhere. So that one is going to be hexanate 2, hex 6. So we've got one more mannose on our high mannose structure. This 1151, is this the same or not? This one's a little bit tricky, I admit. So this is the same because it does have the 1121 in there, but for some reason it's a lot smaller than in the other spectra, but it is still there. Oop. 1151, this one here. So it's quadruply charged again. So it's got a mass of 4,602. The mass of our peptide is 3, 1, 5, 7. Well, my mass is off by 1. 1445, the sugar bit should be. So, no, that's not just another hexose on there. That's too big. Oh, how are we going to do this? I wonder what this is. Can I cheat and look at my answer sheet? Where am I going wrong? can't remember work out what the answer for this one is. I'm going to cheat and look at my answer sheet. It's somewhere down here. Hexnec 4, hex 3 fugose. So, where have I gone wrong? Hexnec 4, hex 3 fugose. So why was I off by 3? So it should have been 1444, apparently. What did I must have calculated something wrong. Try one more time. 1151.27 times 4. So that's with take away 3 to give it a singly protonated mass. 4,602. Is that what I got last time? Okay. I'm getting a different number every time. That's nearly 1444. It should be 1444. What am I doing wrong? Yes, that's probably what it is. Yeah. So, yeah, if I put the decimal places in, it's probably 1444.5, hopefully. I'm not using decimal places. I'm being lazy. Okay. You've solved my problem. So last 3. Top one again. We've got a big 1121, so it's another version of the same peptide. 1175.2. Let's use some decimal places this time. Let's see if we can solve it. 1127.